The nature of electromagnetic waves. All right, so on one hand, we describe light in terms of photons having energy hf and momentum h over lambda. On the other hand, we observe diffraction and interference consistent with wave properties. So one of the most important questions of modern physics is how to make the connection between these two pictures. So the question is light simultaneously a particle and a wave? And we have seen in our discussion of relativity, one important question is what is the effect of gravitation on light? So does light get affected by gravitation? A related question is there an effective mass of the photon? For example, let's think about momentum. Even though we know the relativistic one is gamma m v. So let's say that we introduce the concept of an effective mass for the photon. Effective mass times c, the speed of light, is equal to h over lambda. Effective mass times c square is hc over lambda, or hf. So is it possible to talk about this effective mass of the photon? And basically, we can say that the particle and wave models complement each other, and we will see the Broglie takes this one step further for not only photons but for all other quantum particles as well. Okay, so the wave properties of particles, this was introduced by Louis de Broglie, 1923. Photons have both wave-like and particle-like characteristics, so this led de Broglie to think that perhaps all forms of matter have both properties. This is called the principle of complementarity. Basically, there is a wave that is associated with a particle, a moving particle, at all times. The material particles of momentum p have a characteristic wavelength called the de Broglie wavelength. With the same momentum, p is equal to h over lambda, lambda is equal to h over p. So for p, we substitute the linear momentum, the non-relativistic version, h over mu, and E, the total energy, is hf. Okay, so this proposal by de Broglie was verified by Davison-Germer experiment and Thomson observing the diffraction of electrons. So electrons were treated as particles, but since they show diffraction pattern, that means they have wave properties as well. Subsequently, diffraction patterns of hydrogen, helium atomic beams, and neutrons were also observed. Basically, this statement that a moving material particle with momentum p will have a wave with wavelength, the Broglie wavelength, associated with its motion. So this electron diffraction also led to the development of the electron microscope. With very high kinetic energy, these electrons have very low wavelength. It's 1,000 times better than optical microscopes, so we can easily probe things in the atomic scale using these high technology microscopes. All right, so let's take a look at an example. Calculate the de Broglie wavelength for an electron. The electron mass is rest mass is 9.11 10 to minus 31 kilograms, moving at 1 times 10 to 7 meters per second. So for this first part, we can calculate its linear momentum, the non-relativistic version, its mass of the electron times its speed, u. So that will be 9.11 times 10 to minus 31 kilograms multiplied with 1 times 10 to 7 meters per second. So this gives us 9.11 times 10 to minus 24 kilograms meter per second. Now the momentum of this electron is related to its wavelength. P is equal to h over lambda, and this is of course true when the speed of the electron is much less than the speed of light, while 1 times 10 to 7 is much less than 3 times 10 to 8, so it is in the non-relativistic limit. So the Broglie wavelength we can calculate, lambda is equal to h divided by the linear momentum p. Now Planck's constant is 6.626 times 10 to minus 34 joule seconds. The linear momentum we have calculated 9.11 times 10 to minus 24 kilograms meters per seconds. So this gives us a wavelength. Lambda is equal to 7.27 10 to minus 11 meters. As you can see, it's a very small wavelength for the electron. All right, part B. A rock of mass 50 grams is thrown with a speed of 40 meters per second. What is its de Broglie wavelength? Now we're not talking about a material particle, we're talking about an object. So what is the linear momentum of this rock? It has 50 grams, 50 times 10 to minus 3 kilograms mass. It's moving at 40 meters per second. Therefore, its linear momentum is 2 kilograms meters per second. Now we can use the de Broglie relation. P is equal to h divided by lambda. And this gives us lambda is equal to h divided by p. So we have 6.626 10 to minus 34 joule seconds divided by 2 kilograms meters per second. And that gives us a wavelength lambda of 3.3 times 10 to minus 34 meters. Okay, so this is basically a much smaller than any aperture size, any practical aperture we can produce in the lab. So diffraction from the material wave for a rock moving with the speed cannot be detected. It doesn't mean it's not there, but it cannot be detected because it's way too small. It's impossible to get an aperture size comparable to or greater than this wavelength so that we can see the wave-like properties of this moving rock. All right, so to summarize, we've talked about the nature of electromagnetic waves. We have two visions of light. One is it consists of energy packets called photons, each with energy hf and momentum h over lambda. On the other hand, we see wave-like properties, so it's an electromagnetic wave that gives us diffraction and interference patterns. So the light has both a particle-like and a wave-like character, so these two models complement each other. Light gets affected by gravitation as shown by Einstein's theory of general relativity. And another related question is there an effective mass of the photon? For example, effective mass times c is h over lambda, effective mass times c squared is hc over lambda, hf. Okay, so now, having these observations about the dual nature of light, in 1923, de Broglie came up with the idea that all forms of matter have both wave-like and particle-like properties called the principle of complementarity. principle of complementarity. And we can find the wavelength of the wave that is accompanying a particle as h over p, where p is its linear momentum, mu, in the non-relativistic limit, and it will carry total energy, hf. And this was verified by Davison, Germer experiment, and Thomson by diffraction of electrons. And we have also seen diffraction of hydrogen, helium atomic beams, and neutrons as well. So we can basically see that this suggestion is correct. And by using electron diffraction, actually we can build electron microscopes with very low wavelengths, much better resolution than optical microscopes. Then we compared the de Broglie wavelength for an electron that is moving at 1 times 10 to 7 meters per second with a rock 50 grams moving at 40 meters per second. The question is, why don't we see in everyday life the wave-like properties of matter? Because you can see that the wavelength, the Broglie wavelength for an ordinary object is of the order of 10 to minus 34 meters, which is much less than any aperture size. So these diffraction effects cannot be detected experimentally.